Okay, hi everyone. Thanks very much for joining us for another edition of the Sound seminars. For those of you who don't know me, I'm Giles Ferron. I'm an ocean modeler within the Somisana group at the Egagasini node. And our group is broadly focused on ocean modeling, particularly within South Africa's oceans. And today's presenter is Gustav Rautenbach. So he's been with our group working on ocean models for about a year now. And today he's going to be sharing some of the work he did for his PhD, which was recently awarded. And so in this work, he also used an ocean model to try and better understand eddies which form on the inner edge of the Agulhas Current and the role they play on the ocean dynamics of our east coast. So thank you very much, Gustav, for the presentation, and I'll hand over to you.
No, thanks, Charles. So hi, everybody. My name is Gustav, and as Charles mentioned, I'll be presenting just a paper I'm working on from my PhD, which is titled Frontal Eddies, Coastal Drivers in the Shadow of the Agulhas Current. So I was supervised by Mike Roberts from Nelson Mandela University, Stephen Herbett, Pierrick Penvin, and Jill Dose-Camben from University of Western Brittany in UBO, and LOPS, and then obviously our very own Jennifer Veach from SAEON at the Egagasini node. So for this presentation, I'll just be going over, or I'll briefly introduce the study, followed by just going, highlighting some of the background studies that's been done, and just showcasing some of the research questions that we'll be investigating during the study. And then I'll highlight my methods and materials that I use to obviously investigate the research questions, and then present some of my findings, and then following, I'll just wrap it all up in a nice and simple discussion and conclusion. Sorry, right. So basically, just to give a short introduction, this study investigates the life cycle of frontal eddies from generation to decay on the inshore edge of the Agulhas Current, located along the east coast of South Africa. So you can see that quite nicely on the snapshot provided or showcased. We've got the very warm Agulhas Current flowing along the east coast in a polewards direction. Just past the east coast of South Africa. So specifically, we're going to be looking at frontal eddies, which are rotating bodies of water that forms on the boundaries of these strong currents. In our case, we'll only look at the inshore frontal eddies. So we'll be investigating these frontal eddies, which I've pointed out here with the yellow arrows. So we're going to be investigating these frontal eddies using a three-dimensional ocean model, an eddy detection algorithm, particle tracking, potential vorticity, and the Richardson number. So these tools provide quite an exhaustive analysis of the frontal eddies and how they influence the coastal circulation, where these valuable marine protected areas have been designated. So I've just showcased some of these valuable marine protected areas on the east coast that are often influenced by these eddies. These marine protected areas are obviously important because they host a variety of fauna and flora and provides a nursery area for various species. So just to provide some background, the Agulhas Current is the western boundary current of the Southwest Indian Ocean and is the main oceanographic feature along the east coast of South Africa, where it originates at roughly 27 degrees south. It propagates, or it transports a large amount of warm and salty waters in a polewards direction. And it transports, And then this is showcased here on the schematic. As you can see, the Agulhas Current propagating downstream, and then it retroflects here at the southern tip of South Africa, then propagates in eastward direction. So unlike downstream of Port Elizabeth or Kiberga, which is the portion of the Agulhas Current that is relatively unstable, the upstream section, which is where we'll focus the study on, is remarkably stable and forms a narrow jet stream. Here, the Agulhas Current veers less than 15 kilometers on either side of its mean position, which is attributed to the steep and straight topography of the east coast. This is, of course, with the exception of the passage of frontal eddies that originate from the KwaZulu-Natal Bight. So the KwaZulu-Natal Bight is a portion of, is a section that falls between Richards Bay in the north and Durban in the south. Where the coastline recedes and the continental shelf extends offshore, it forms a sheltered embayment with weak but variable surface currents. So where the coastline recedes, when the Agulhas Current flows past Richards Bay, it becomes unstable. these instabilities rolls into cyclonic frontal eddies, or locally known as Natal Pulses or Durban Eddies. These eddies are associated with the Natal Bight coastal countercurrent, which you can see with the arrow where it says NBC3, which basically propagates in an opposite direction or equator direction. Yeah. So Natal Pulses has been quite a major focus in the past decades due to their large spatial and temporal scales and are therefore relatively well understood. Their generation is believed to be linked to the offshore mesoscale eddies, pulling the Agulhas Current waters offshore, which allows the large cyclonic meanders to develop in the KwaZulu-Natal Bight, which grows into Natal Pulses. Due to their large size, they can disturb the entire coastal environment along the east coast. They are long-living and provide and propagate past Port Elizabeth, where they can lead to an early retroflexion of the Agulhas Current. So I'll just showcase here some snapshots of the sea surface temperature. Can you really see these large meanders along the east coast, and they propagate quite far downstream, where they can cause early retroflexion. However, the Durban Eddies, so with the recent advancements in satellite observations, it has allowed us to study the finer scale dynamics, such as the Durban Eddies. So Gustav in 2016 did show that the Durban Eddies are much smaller and far more frequent than Natal Pulses, occurring 55% of the time. Well, roughly 55% of the time. And has an average lifespan of roughly 8 days, which reoccurs every week, thus making their presence semi-permanent. They have a far shorter lifespan and often get stuck at the site of generation. So that's a Durban eddy, which is shown here. They often just can get stuck there. However, in some cases, they can break free from the KwaZulu-Natal Bight and propagate downstream. Obviously not as far as the Natal Pulse, because they will dissipate along the coast. During their presence, they, it was pointed out by Gustav in 2016 and Robert et al. In 2010, that they also drive upwelling along the inshore edge of the Durban eddy, and they're properly enriching the coastal environment. However, due to limitations with the in-situ measurements and satellite observations, it has caused several challenges for us to study these finer scale dynamics. So we therefore have quite a lot of gaps in our understanding of these dynamics. So, for instance, in-situ measurements are very expensive, as we all know, and they lack spatial resolution. In the time series I've got shown here, I've got a thermistor array, which you can see the temperature evolves over time. And this was deployed offshore of Durban, just to showcase during the propagation of the Durban eddy. And we can quite nicely see that it uplifts cooler waters in the core of the eddy. But obviously it's quite difficult to get a full or complete three-dimensional view of the eddy. So they lack spatially because we only have one spatial point measuring the jump. However, and satellite observations are often obscured with cloud cover, especially over western boundary currents, making it quite difficult or even impossible to get an image of these eddies, or these eddies life cycle along the coast. So yes, we can use like a blended product, but they often smooth out the finer scale dynamics, or even lack spatial resolution that is required to resolve these features. This is why, in our case, we'll be using a three-dimensional ocean model to study the inshore frontal eddies of the Agulhas Current. So for my research questions, we'll be looking at just the frequency of the eddies, like how often they occur, what their characteristics are, and how do they influence the coastal circulation. So to do this, as mentioned earlier, I'll be using a 1 kilometer crocker model simulated for this study. We configured a low resolution model at roughly 3 kilometers resolution, which is shown on the black mesh. It's quite a large domain to really capture all the important features that contribute to the Agulhas Current. Its boundary conditions, or the model gained its boundary conditions from era 5 at the surface, glorious 12 at the boundaries, and then SRTM at the bottom. So the 3 kilometer model essentially then provided the boundaries for the 1 kilometer model, which was run for 8 years, including a 3-year spin-up. The reason why we downscaled is just to ensure that we can resolve the frontal eddies satisfactorily. Yeah, I'm not going to go into any detail with regards to the model evaluation for this presentation. So let's just assume that it's accurate. Next, we developed or used the angular momentum eddy detection algorithm, which is basically a hybrid eddy detection algorithm, and it uses both the kinematic and geometric properties of flow to detect the eddies. The main reason why we used AMIDA is simply because it is based entirely on the fluid flow or the fluid dynamics. So essentially, small eddies that does not have a strong sea surface signal can be detected. And it's quite useful, especially for when the eddies are generated or dying or dissipating. Yeah, I'm not going to the formulations, but if there's any questions, please do not hesitate to ask me at the end. So yeah, I've just shown a snapshot of AMIDA detecting and tracking an eddy. So yeah, we can, yeah, I've just got an eddy case here. In the color, I've got the relative vorticity, which is, and then the surface current superimposed on black contours, black arrows. Essentially here, the black ellipse shows the eddy detected on this day, and the magenta ellipses shows the tracks of the eddy in the past and in what it's going to do. So for those that don't know, relative vorticity is really just a rotation relative to the Earth, where the negative or the blue is cyclonic circulation and the positive is anticyclonic circulation. So that's clockwise rotating and anti-clockwise. But anyway, so what I really wanted to show you here is that we can track the eddies from one day to the next. And also what is quite interesting is that the orientation of the eddy changes from an elliptical shape at the generation in KwaZulu-Natal Bight here to a more circular shape as it propagates downstream and eventually dissipates. So we applied our eddy detection algorithm to the entire model run. Obviously, I had to do some post-processing. So basically, I removed eddies that had a shorter lifespan of 4 days because they were considered noise. And I removed eddies that propagated past Port Elizabeth because we considered them as anomalous events or Natal Pulses. There were only 2 of those events. So yeah, it was just really large anomalous features that we removed. So, but in total, we detected 366 eddies over 5 years, which gives us roughly like an eddy every 5 days. So it's obviously quite frequent, these events, or even semi-permanent, as mentioned earlier. So yeah, we can quite nicely, so I've got a plot here, which is really just the displacement distance, sorry, the lifespan of the eddies as a function of the displacement distance. And we can see I've got a bimodal distribution, which points to 2 different groups of eddies. We separate them based off the displacement distance and name them stationary and propagating eddies. The stationary eddies are on the peak or the group A, and then the propagating eddies are group B. Yeah, and basically we also detected less stationary eddies versus the propagating eddies that we detected like 276 or 290 eddies, sorry. Good job. So now that we have our 2 different groups of eddies, we plotted the probability density of the stationary and propagating eddies to determine where they are generated and where they are dissipated. So the stationary eddies are on the figure on the on the figure on the top. You've got the stationary eddies. At the bottom, you've got the propagating eddies. On the left, you've got the generation sites, and on the right, you've got the dissipation sites. And basically, just to summarize, the stationary eddies distribution is relatively cloudy and spread throughout the KwaZulu-Natal Bight for both its generation and dissipation, whereas the propagating eddy has a more concentrated distribution, which is concentrated offshore of Durban for its generation and downstream of Durban for its dissipation. So yeah, so this kind of points to the idea that the stationary eddy remains within the KwaZulu-Natal Bight, which you can see here on the left-hand side, where its propagation or kind of just remains as a blue dot in the center of the Bight. Whereas the propagating eddy detaches from the KwaZulu-Natal Bight and downstream and propagates downstream, where obviously we have numerous marine protected areas. So there's obviously a function of time. So obviously not in all cases your propagating eddy will go all the way down, but it will propagate downstream of the Bight. So yeah, so just what is really cool about the eddy detection algorithm is that we can extract quite important parameters of the eddies that, yeah, of the eddies. So here I'm just showing the mean radius on the left, the mean azimuth velocity in the center. The azimuth velocity is just a circulation around the eddy, and then the mean amplitude is on the right. These are all plotted as a function of time, so how it evolves over time. Yeah. And the radius basically indicates the size of the eddy, whereas the azimuth velocity and the amplitude is indicative of the eddy intensity. The blue line represents the stationary eddies, whereas the red line is representative of the propagating eddy. So basically, when the eddy generates, it increases in size and intensifies, reaching its peak intensity and size, after which it rapidly dissipates where it decreases in size and intensity. So this is true for both the stationary and propagating eddy. I did, however, just want to point out, when you look at the plot A, so that's the radius, you see there's extra lines there. We've got a dashed and dotted line, which showcases the major and minor axes of the eddy. So that's really like your so it's just the major and minor axes. And what is interesting is how these axes start to converge as the eddy grows and changes from a elliptic to a more circular shape. Yeah, that's kind of the main idea. But the main message here is that the stationary eddy is smaller, less intense, and has a shorter lifespan compared to its propagating counterpart. So now that we have really kind of got to the point that they are quite frequent and we have different types of eddies, we're going to look at the characteristics of the eddies. However, due to the frequency of these eddies, we can focus on one eddy case because we can kind of assume that all the processes takes place for all of them, or the same processes takes place for all of them. So here we're going to, I'm just showing this snapshot again. Same case study, but in this case, I would like to go into a little bit more detail of this figure, and we can quite nicely see that it generated in the KwaZulu-Natal Bight. It grew and intensified till this time step here, where we're at now, on 3 March 2006, after which it started to propagate downstream. So we will, however, be looking at this cross-shore transect that's in black, and we'll be looking at the vertical, we'll be looking at the vertical structure of the eddy, using a little bit more, using potential vorticity. So potential vorticity, without going into too much detail, it's a very powerful tool in oceanography because it gives us an approximation of the flow field. So negative potential vorticity is cyclonic circulation, which is clockwise in the southern hemisphere, and it is associated with uplifting the isopycnals or the density contours. So as I've mentioned, potential vorticity is a very powerful tool in oceanography because it does provide us with like a approximation of the flow field. So negative potential vorticity is cyclonic circulation or clockwise rotating in the southern hemisphere, and it is associated with the uplift of isopycnals. We can see these uplifting isopycnals in the snapshots here, where we've got the potential vorticity on the left, but you can also see it in the temperature snapshot, where we've got cooler temperatures being uplifted, but also you can see the doming isopycnals. These are different depths, but I just thought the snapshot of temperature is quite nice to show alongside the potential vorticity for the non-potential vorticity people out there. So obviously the opposite is true in the case of negative. Ooh, sorry, I messed up here. Sorry, negative potential vorticity is cyclonic. I don't know if I mean, and then that's obviously clockwise rotating, and it leads to uplifting the isopycnals. Whereas the opposite is true for positive potential vorticity, where you'll have anticyclonic circulation and like a deepening of the isopycnals. In our case, it is quite clear here that the eddy is associated with a strong cyclonic circulation, which is situated in the surface layer. So the surface layer here is defined from the 1026.0 isopycnal here, and the thick black density contour that extends to the surface. So that's our surface layer. And then we've got a middle layer, which is the layer just below that. So that's 1026.0 to 1026.6. And below that, we've got a 1026.6 to 1027.7, that we call the bottom layer. So we've got those 3 layers. And really the idea here is that we can see that the cause of these potential vorticity circulation decreases with each succeeding layer. So you can see that the circulation decreases with each layer. Yeah, so that's it. And yeah. Oh, and then these cores tend to remain in these layers throughout the eddy's life cycle, and when they die, so does the eddy. So yeah, so here I've just got that short animation of us seeding the eddy with particles. We seeded the eddy when it reached its azimuth velocity, so that was the peak intensity of the eddy. And we could backtrack and forward track these particles to kind of determine where they are coming and where they are going. The particles were seeded from the surface down to 1,000 meters depth, and we seeded like 1.2 million particles to basically ensure that we can analyze all of the dynamics related to the eddy. And I just actually wanted to show it again. But so you can see that most of the particles stems from the Agulhas current. They essentially form the eddy, which is that point where we seeded it, and then the eddy propagates downstream and it loses these particles by filamentation, or at least being torn apart by the Agulhas current and the land boundary. Yeah, so that's really what you saw there. Okay, now another animation here. Instead, this time we're looking at the potential vorticity. So this is the mean potential vorticity within each of the isopycnal layers. So we've got the surface, middle, and bottom. And yeah, it's quite cool here because you can see that the eddy gained its circulation from the Agulhas, or the inshore frictional boundary layer of the Agulhas current, which extends here as a filament. It forms these small sub-mesoscale circulations that essentially merges together to form the big eddy, and then propagates downstream and then gets torn apart by the Agulhas current and the land boundary. Yeah. Oh, sorry. Sorry, I just lost my place here. Cool. And then for the last section, like how do we how does the eddies really influence the coastal circulation? So here is just a time series really of the Richardson number. And on the top, basically, you've got the surface layer, and the bottom, in the middle, you've got the middle isopycnal layer, and then at the bottom, you've got the bottom isopycnal layer. And this really just showcases, from the left-hand side, you've got the when the eddy gets formed, or where it gets it from. And then when the eddy has formed in the second column. And the third and fourth columns is really when the eddy propagates downstream, and then the fourth column represents when the eddy has dissipated. And these are all just the particles that was trapped within their respective layer. Just to kind of clarify what the Richardson number is. So the Richardson number is a non-dimensional number that basically compares the stratification and the vertical transport. So if you have a Richardson number that falls between 0.25 and 1, you have mixing, or vertical mixing, I should say, which I think we can all agree on. Here we see a lot of that. Yeah, so it's quite clearly that the eddy leads to quite a bit of mixing along the inshore edge, particularly. But also, what is quite interesting in that you can see on plot D and E is how you have particles that extends back into the KwaZulu-Natal Bight, which kind of suggests that the eddy is quite clearly associated with a countercurrent that essentially just transports particles like along the coast. So it assists essentially with the longshore transport. We also have we can see at figure D, and on the right column, there's quite a lot of particles that advex offshore. So it obviously assists with the cross-shore transport between the Agulhas, or the offshore, and the coastal region. But then also, and then it obviously drives vertical mixing, which I think is quite clear. And then just to conclude here, we'll discuss. So I think it's quite clear that that the eddies were detected quite frequent, that they are frequently occurring. But they gain their sources from the frictional boundary layer of the Agulhas current, as we saw with the potential vorticity, or the from the inshore frictional boundary layer. And then the eddies are surface intensified, and they are associated with quite a strong cyclonic circulation, which uplifts the isopycnals in the core of the eddy. We also detected two different types of eddy, which is the stationary and the propagating eddy. the stationary eddy is not as common as a propagating eddy, or as much as we identify them, but also they are smaller, weaker, and shorter living compared to the propagating eddy, which is quite large, intense, and long living. Yeah, and then obviously due to the frequent occurrence of these eddies, we can kind of expect that they can greatly influence the East Coast, where numerous marine protected areas have been designated. Yeah, and they obviously assist with the cross-shore and along-shore transports, as we saw with the particles, but then they drive vertical mixing, which can favor primary production. Yeah. So yeah, that's the presentation. Thank you. I don't know if there's any questions.
Thank you so much, Gustav. Yeah, I found that very interesting personally. So yeah, I think
thanks.
if anyone has any questions, please feel free to. I see. So we got the. If anyone has questions, you're welcome to raise your hand. Or if you want to pop it into the chat, you can. But while we're waiting for people to put in questions, Gustav, I was just wondering, as a very much non-expert in eddies on the East Coast, something I have heard about is that they're related to the sardine run in some way. Would you be able to shed any
Yeah.
light on that and how that works, or if it works, or is there a relation? Would you be able to comment?
Well, I've heard that there's relationships between it, but I do think that that they are associated with the countercurrent. I believe some of the ideas are that the sardines at least can kind of because they always have to fight the Agulhas Current. So in the case of a Durban Eddy or Natal Pulse or anything like that, it forms a coastal countercurrent, which I think they can kind of use that as an easy way to kind of migrate further up north the coast on the East Coast. That's kind of my idea. That's kind of what I thought, at least. But yeah, I don't know if there's I know Mike Roberts did quite a lot of studies yeah, but I also think that there's some section, I think it's the waterfall bluff, that you always I think you believe that if there's an eddy there, then the gates are open and basically they can use that to kind of then go through and go all the way to KwaZulu-Natal, which I think we just had one. I think we just had a quite a big sardine run happening. But yeah, that's kind of my understanding of them.
Thanks, Gustav. So I see a question from Marjolaine. Can you expand on the generation mechanism for the eddies? It looks in your case study that there is an anticyclone offshore. Or Marjolaine, if you're free to jump on the call and add to it if you like. Gustav, would you like some? Yeah.
No. So yes, I think there's kind of like, because you have like these large mesoscale features that can form, and those are like your Natal Pulses, and then you have the much smaller Durban Eddies, which is what we looked at in our case, that leads to the generation of them. Well, they have kind of like, yeah, so the smaller eddies, like the Durban Eddy, are formed when the Agulhas Current becomes unstable at Richards Bay. That leads to I suppose a baroclinic and a barotropic instabilities, and that eventually grows into the Durban Eddy. However, in the case of a Natal Pulse, I believe, well, not I believe, but I believe that there has been studies out that kind of suggest that offshore mesoscale eddies pulls the Agulhas Current further offshore, and that gives them space to grow into these larger features. That at least is my understanding of it. So yeah, I don't know if that answers the question.
I'm gonna mute. Hope you can hear me.
Please do.
Yeah, I mean, you're only looking at the smaller eddies, so I'm just wondering if the one that propagates have different generation mechanisms.
Oh, so yeah, so that was actually like a very good. We actually wanted to go into that a little bit more detail, but I suppose that's always a question for after this. Like what makes the propagating eddy sort of propagate versus the stationary eddy remain stationary. And I think at the moment we kind of have our suspicion whether we have like where they kind of where the stationary eddy kind of does not have enough vorticity or circulation, whereas in the case of the much larger eddy, it gains a lot of like vorticity, like circulation, and then it episodically flushes downstream, and that's when it like propagates. But yeah, I'm not too sure. We didn't go into too much detail about that, unfortunately.
We have another question from Chantel, who's not an oceanographer. Well, there are very few people on the call who are, so you're not alone. Will the will these counter currents be around all the time, or only when the eddies are propagated?
I think they form when the eddies are there. So it's not necessarily just when the eddies propagate. So even if you have a stationary eddy, or there will be a countercurrent essentially. But when they are propagating, you'll also then obviously have a countercurrent.
Yeah, I mean, just from mine, it's also sparking my question from me is, if you have a countercurrent, does that basically mean that you have an eddy? Like, are they one and the same? Like, is it
So my
possible to have a
understanding
countercurrent without an eddy?
No, I don't think so. I think, well, I
Yeah,
mean,
it's basically one and the same. Well, it's like the inshore limb of the eddy, almost. Or
yeah,
not?
yeah. And I think then that kind of extends further northward. That's kind of my understanding. Whether you have it there without the eddies, maybe, but maybe it's not so intense then. Maybe the eddy kind of just fuels it, but I don't think so. I think the eddies are there and they form the countercurrents.
I was wondering if I could come in there because
Please do.
Please.
it's a little bit what Sonia Hay has looked at in her papers on the coastal current, the countercoastal current, that definitely the eddies intensify the current and make it reach further north. And because you have essentially a semi-permanence of eddies, you have this countercurrent in the mean. But I had another question, if I may.
Please do.
I was quite interested in when you showed those very small submesoscale eddies who merge with the propagating eddy.
Yes.
And what happens then? Does it causes an intensification in the eddy in its intensity and size, or what happens?
I can only assume so. But yeah, I'm not 100% sure, but they are very interesting. And I suppose the more of these little clusters you have of submesoscale eddies, the more intense your eddy will become, essentially. Or that's kind of what I would assume would happen, but I could be wrong. But it's very interesting. I think the animation shows it quite nicely. Also, yeah. Especially if you look at like the bottom and the middle layers, you can really see like the eddies being like these chaotic generation of them, and then kind of like merging together, which I thought was quite interesting. But I can't for certain say if it's I think Jonathan Gula did look at submesoscale eddies within the eddies, and they would essentially just help uplift, or like they would kind of like not supercharge, but like almost boost the primary production, well, the vertical transport in the eddy, really, which I thought was quite interesting.
We have a question from Sifiso, who's asking, what do you think would happen if you were to remove the impact of the Agulhas current on the mesoscale eddies? Would that affect their size or age, experiment-wise? Don't know, Sifiso, if you want to jump on and elaborate.
Hello.
No, because yes, hi, thanks.
No, I'm just asking if he were to do an experiment looking at the mesoscale eddies, on the southeast coast of South Africa, if we just remove the Agulhas Current, just do an experiment, would it affect the longevity and the age of the AD? And how did it affect the connectivity? Maybe the AD be more, would it stay longer or would less propagate? Something like that. That is my question.
I mean, very speculative of me to answer that, but I suppose, would you even have eddies if you have no current, sort of thing? Because yeah, I think that yeah, I'm not quite sure. I think maybe the like maybe you won't have eddies being generated at all. Maybe they will be less intense, or yeah, I can't answer for certain.
If you had to design the experiment, what would you do? How would you design it? How would you remove the Agulhas Current from the model?
To be honest, I'm not sure.
Yeah.
Yeah,
So Jenny,
turn it
so
off.
Jenny did something like, yeah, looking at the impacts, removing the Agulhas Current on the west coast by like building in an artificial, like very large, like ramp off on the east coast. Potentially, you could do something like that, like further upstream in like the Mozambique Channel or something, deflect the water, but it becomes a difficult thing to interpret. But yeah, thanks for that question.
It's an interesting question. Yeah.
Do we have
thank
any
you.
further questions for Gustav? No more. I think yeah, thank you very much for all the questions and interesting dialogue, and for Gustav for your excellent presentation. So
No, thanks for
yeah, and then finally, last point is that we have a last seminar. Sorry, the next seminar will be on the 7th of August. I think still to be determined.
Thanks, everyone. Thanks for listening to my talk.
Thank you. Bye.
Yes.